Okay, so let's quickly review what we were talking about last time.
Okay.
We were discussing how to analyze error when you're detecting a signal in noise. So what we had was that you have signals S0K and S1K. One of those signals is transmitted. Them plus noise are passed through a detection filter HK. And then we make a decision. And the decision is based on a threshold where if it's greater than Z, if the value at the output of the filter is greater than Z, we choose 0. Less than Z, we choose 1. So, we showed that the output of this match filter at time NB, so NB is the number of samples contained in each of these signals. At time NB, the output of this filter is a Gaussian random variable, represent that with n, with mean either S0 or S1, and variance, sigma squared, where I define all those terms as follows. S0 is the noise-free output of the filter if S0 is sent. So that's S0 is the convolution of S0, K, and the filter evaluated at time NB. And S1 is the signal S1 involved with the filter evaluated at time NB. So because noise is additive and because the filter is linear, these noise-free components will be added to the noise at the output of the filter. So therefore, this is a noise is a zero mean random variable. So therefore, the output of the filter will be a Gaussian random variable with one of these two means, either S0 or S1, and variance sigma squared. Last time I told you variance was given by N0 over 2TS, where N0 is some physical constant related to the noise power spectral density, and TS is the sample time, sum over H of K from I equals 1 to NB. This is actually, there's an error here. I'd just like to point that out. This is not the sum from 1 to NB of H of K, it's the sum from 1 to NB of H of K squared. So that means variance obviously can't be negative, even though H of K can be negative. It doesn't affect anything else we did because the values of H that we used last time are all equal to 1. So 1 squared is still 1. Okay. Then what did we do? We said, okay, our job is to distinguish between, or our job is to figure out the probability of making an error. So if 0 is sent, then we have this Gaussian random variable with average S0 and variance sigma squared. So drawing a diagram of that, here's S0, and we have a Gaussian distribution like that. So this is the PDF of the output if 0 is sent. And what we're going to do, there's going to be some threshold Z, let's say it's there. And if if my received value, I think I call that phi. If phi is greater than z, then my decision is correct. Because on this side of z, I decide 0, and on this side of z, I decide 1. So therefore, if phi is greater than z, my decision is correct. If phi is less than z, I have an error. So the weight of this tail of the probability density function is equal to the probability of error. Similarly, if I send a 1, then I have a Gaussian random variable with mean S1 and variance sigma squared. So let's say the mean is over here for S1. And again, Z is over here. Then on this side of Z, I pick 1, which is correct. And on this side of Z, I pick 0. So the probability of error, given that a 1 was sent, is in this tail. So my total probability of error is equal to the probability of error given that a 0 was sent times the probability of a 0 plus probability of error given that a 1 was sent times the probability of a 1. So this tail weight here is that probability, and this tail weight over here is that probability. And these are given to you the probability of 0 and 1, and most often they're equal to each other and equal to 1/2. Because zeros and ones are usually equally likely. Okay, we went through an extensive derivation to show that the probability of error given 0 can be expressed in terms of a special function called the ERF-C, or error function complementary. That was given by, we showed last time, 1/2 ERF-C S0 minus Z divided by the square root of 2 sigma squared. And similarly, probability of error given that 1 was sent is equal to 1/2 ERF-C Z minus S1. Note that the terms are reversed here because we're looking at the other side of the tail. Z minus S1 divided by the square root of 2 sigma squared. So you can take those, combine them in here, and actually calculate a probability of error. So let's have a couple examples. Let's have a plug-in example that we had from last time.